Session, for talks in the session, each talk. So it's first talk. The first talk is rate one. Some fair extract of hashing from PH by Pedro Branco, Nico Jotri, San, and Eiichiro Fujisaki.
Yeah.
Okay. Sorry.
Yeah. Thanks for the introduction.
Talk.
Yeah. Thanks for the introduction. I just wait. Why is this? Okay. Okay. So, hi everyone. I'm Riccardo, a PhD student at CISPA, and I will present our work on fully local extractable hashing from decisional Diffie-Hellman, and we'll see why this primitive is interesting and how we build it from PDH. So yeah, I'll start with some background and tell the applications of this primitive. Then I'll explain what this primitive is and how can we construct it. First of all, let's have a broad overview of the field of research, and actually it's not in the title, but the main topic is related to snarks, and I'll define what the snarks are, but the main point is that they are known in the random oracle model, but otherwise are impossible from falsifiable assumptions in the plain model. And so what the field of research did was to focus on subclasses of snarks, in particular for P and for the language batch MP. And they built these snark for these subclasses from correlation intractable hashing, and then via more recently via this fully local extractable hash primitive. So there are a lot of acronyms. I'll try to explain most of them, all of them. And so the point is that the main result is barks, and actually rate one barks. And there has been work to compile high rate barks with this SEH, so extractable hashing, to compile them into rate one barks. And there's been work by Debada et al. That builds it through this fully local somewhere extractable hashing. And they did it from LWE, and we do it from PDH. So what are snarks? They are succinct, non-interactive arguments. So let's have an MP language which has a circuit for verification, and we want the prover to be able to generate proofs that an instance X is in the language, so that the verifier can read this proof and decide accepts or rejects. And the main point is that we want this to be succinct. So we want the verifier computation time and the proof size to be very small. So yeah, and the main property that we want is soundness. So if the prover is trying to cheat, the verifier will catch it. And this is an argument, so it's against efficient provers. And we remark that there is no hiding or zero knowledge requirement here. So let's define what are barks, which are batched, is a short for batch arguments. And in this case, we have k instances, x1 to xk, with their relative witnesses. And we want the prover to send a short proof to the verifier. And the verifier will be able to decide if all of the instances are in the language, or reject if at least one instance is not in the language. So since we don't have the hiding requirement, the trivial stuff that we can do is just send all the witnesses and delegate all the verification to the verifier. But this has a large communication cost, k times the size of a witness, and we want to be able to have more succinct communication with respect to the amount of instances. So, for example, we would like to have a polylogarithmic dependence on the number of instances. And a remark, we could build batched arguments from snarks, because deciding if all the instances are in the language is still an empty language, but we want to do it without random oracles, so we can use the general snarks. And in particular, we are interested in write1 barks, where write1 means that the proof that the prover sends is as small as a single witness. So let's say the witness size is m, and we want the proof to be m plus some polylambda. And why this is an interesting primitive? Because it allows us to concatenate many barks together. So we want to prove many statements of even possibly different languages, and so we prove them, and then we can prove that the verification algorithm, the barg, will accept them and compact them in another proof, and at each layer we just get an additional polylambda instead of a multiplicative explosion. So, like, other applications are incrementally verifiable computation, which is a strengthening of the delegation of computation task, and in which we have a client who sends a server a function and an input and wants the server to evaluate it. And in the I2C setting, the client wants to be able to get constant updates from the computation. So the server must be able to say, this is my state, and this is my proof of the correctness of the state. And then also aggregate signatures. We have constructions from mainly LWE, using the building blocks of any barg, any non-write1 barg, and we can turn that into write1 bargs via SEH and LWE, FHE, and recently there is also an instantiation from DDH. So what is this fully local extractable hashing? First of all, what's extractable hashing? So we want to hash a string of n bits where we can extract a chosen bit, a chosen position. So we fix I star. There is the setup algorithm that generates hashing key and trapdoor. And with the hashing key, anyone can compute the hash. And we, with the trapdoor, can extract the I start position. And this is a usual hash, and we want to be able to open to any of the position, not just I star, of course. And yeah, they exist from example from FHE or from rate one oblique transfer. And if you want, we want to do to extract multiple bits, we can just repeat this construction many times. And this will give us a hash which is long at least m, which is like we cannot do lower than m because we have to extract the indices, and also the opening will grow in size with the number of extraction indices. So fully local means just that the opening will not depend on the number of extractable positions. And so what the hashing procedure does, it generates the hash value, but also a very small digest. And the opening procedure also generates a very small opening. And so the verifying procedure is super efficient and super short. So like all the components in this gray box are of polylambda size and time. And the only thing that we have to do is there is an algorithm that verifies the consistency of this small digest and the hash h. And rate one just means that this hash is as short as possible, so of length m plus polylambda. And so, yeah, again, what we are doing is we are building this rate one fully local SCH from any barg and any SCH plus DDH, and both of those primitives can be built from DDH, so we get rate one bargs from DDH, which was a result already known by the Panetta and Pass paper, but they're not actually rate one, they're rate 1 plus 1 over lambda. So ours is a bit better. So how does the construction work? So the idea is that we take the input x, and we the short digest will be just some extractable hash at a constant number of positions, while the longer hash will consist of the encryption of the extractable indices, where we compress the encryption. So we are kind of using a rate one encryption of the bits at the position where we want to extract. And yeah, in particular, we use Elgamal encryption. And if you wanted to encrypt the bit x, the ciphertext will be shared key, let's say, times g to the x. And this will allows us to do compression, in the sense that usually we send C0 and C1 for Elgamal, but if we are encrypting bits in this way, we can just send the header C0 and a single bit instead of C1. So what's our hashing key? We select m secret exponents and compute the HIs, and then we sample n random values, random exponents, where n is the size of the input. So our hashing key, our matrix will be very, very large. And the first row will be just the header rows, and each other row will have will correspond to the Elgamal public key, but when we want to extract, we multiply with an additional G. And now we see why we do that. And so what do we do when we want to hash? Like let's say our vector is a size 4, and we want to extract at position 2 and position 3. So we put G at in the second column and at the third column, and we exponentiate each column by the relative xi value. And so this is the result. And we start by multiplying these metrics all together. And we do it in, let's say, a tree. So we multiply 2 columns by 2 columns. So we first multiply first and second, and then third and fourth. And then we repeat it again. And this will be our final ciphertext, which will be an Elgamal ciphertext. So given our secret key, we can decrypt the indices that we want to extract. And so then we compress this ciphertext into our 8-1 ciphertext. And what we need to add is that the small hash that we add, so the ACH of X and this right-one ciphertext are consistent. And we do that by computing barks that all the steps in this computation have been carried out perfectly. So we hash all the intermediate matrices into into many hashes, and each of these hash is extractable just as a constant number of positions, so it will be for lambda. And for any time step t, our bark statement is that the matrix obtained at step t plus 1 is just the product of the two columns of the matrix at time step t. And so this is an index statement, and we can do a bark of this statement with respect to the hash of X and the hash of all the matrices. And so the short digest will be short because it's extractable at a constant number of positions, and also all the bark proofs will be short. The extractable hash is right one because of the compression procedure. The only downside is that this CRS, so the hashing key, is very large. But when we turn this into a rate 1 barg, we will get a rate 1 barg with large CRS, but we can shorten this by recursively computing bargs. And so in the end, we will get rate 1 barg with short CRS. So yeah, the overview of the results is that we have this rate 1 fully local extractable hash function from the DH, obtained by barging together the local computation of the hashing procedure, and we get then rate 1 bargs from the DH, and give this generic transformation of long CRS rate 1 bargs into short CRS ones. And so that's it. Thanks for the attention, and if you have questions, I'm happy to take them. Oh, look at that.
The reconstruction in typing without using particle.
Like, I mean, what do you mean? Like, because, yeah, this, I mean, the hash, yeah, we get the exact double hash algebraically, right? You mean that there could be a way to generate also the short digest algebraically? I don't know. We didn't think about that, but I'm not that sure. I mean, yeah. I don't think so, but we can try to look into that.
blockchain by moving and shifting, but unfortunately, the authors cannot.
I'm sorry, Ken. How to use the presenter view? I have to use the
Oh, you want to see it in words? Are there notes that are part of the book and part of the PowerPoint?
Yes,
I see.
I can take my.
I'm sure we can do. I'm sure we can do this. Just let me say, maybe this. It's okay. It's because the screen is duplicated instead of being shared.
Yes, I can. I will not use my computer. I just use.
I think we just need to figure out instead of duplicating this. Okay, who's a Windows user who knows how to
I can use this.
copy the screen rather than? But I don't know how to plug that in. Oh my god!
I can.
No, you can't.
I will not use this. I just.
Oh, you just want to see? Okay,
Yeah.
thank you. Excellent.
Okay, thanks for the introduction. Good afternoon. I'm the proxy speaker, and I will make the presentation on behalf of the authors, Yiming Li and Shengli Liu, who are regrets not being here in person to give the talk. And the title is 10 per million hash from lattices and the application to redactable blockchain. So let's come to the introduction first. Blockchains are originally designed with the property of immutability. That is, the message stored in the blocks cannot be changed. However, this might not be friendly to the healthy development of blockchains. For example, once some illegal or malicious messages are uploaded to the blockchain, then it cannot be removed. As another example, once some personal information is stored in the blockchain, then it is hard to erase them. So this concerns draw an interesting interest in redactable blockchains, which allow secure and controlled after-the-fact modifications of the content. And according to the existing results, actually we can upgrade a traditional blockchain to a redactable one by using chameleon hash functions in place of the traditional hash functions. And more precisely, one can use the trapdoor of the chameleon hash to find collisions so that the content in blockchain can be modified without changing its hash values. Generally, a chameleon hash consists of 3 algorithms. The setup algorithm generates a public parameter and a trapdoor, and the hashing algorithm computes the hash value of a message with the help of a randomness. And the adaptation algorithm uses the trapdoor to adapt a hash value of m to a hash value of m prime by outputting the corresponding randomness r prime. And roughly speaking, with trapdoor, one can efficiently find collisions by invoking the adaptation algorithm. But without the trapdoor, it is collision resistance. And there are several kinds of collision resistance defined for chameleon hash. The full collision resistance, or full CR for short, is the strongest one. And chameleon hash with full CR is turned out to be more desirable for the redactable blockchain. Recently, there are several chameleon hash with full CR are proposed. However, they are either based on DDH or D-log assumptions, and thus not quantum safe, or rely on the random oracle model. Besides, these chameleon hash all use heavy tools like extractable NISIC in their constructions. So it is natural for us to ask, can we design a post-quantum chameleon hash serving for the redactable blockchain in the standard model, and especially without relying on NISIC proof? In this work, we will answer this question in the affirmative by designing chameleon hash from lattices in the standard model. We provide a new approach to the question, and let's show its high-level ideas. Actually, we find that redactable blockchains actually satisfy some nice properties. And when taking these nice properties into considerations, the security requirements for chameleon hash can be weakened. And this makes possible simpler constructions of chameleon hash. First, we have 3 observations about the chameleon hash-based redactable blockchain. Our first observation is that each block is in fact indexed by a unique identifier, like the timestamp or the hash value of its previous block. And consequently, we add the unique identifier or tag TOR in the description of the blocks. And additionally, we take TOR as inputs for the evaluations and the adaptations of chameleon hash. This gives us a new variant of chameleon hash called tagged chameleon hash. And we define full CR for tagged chameleon hash. More precisely, in the security experiment, the adversary can make multiple adaptation queries to ask the challenger to adapt the hash value of m to hash value of m prime with respect to tag TOR, and gets the corresponding randomness r prime. We use a set Q to record the tag hash message tuples. And finally, the adversary outputs a collision, and it wins if the message m star is different from m prime star, and their hash values are the same with respect to the tag TOR star. Moreover, the tuple TOR star h star m star is not in the set Q, which means the tuple is fresh and never appears in the adaptation query phase. Such tagged chameleon hash with full CR also serves well for redactable blockchain. Then our second observation is that each block in the chain has a chameleon hash value and a tag TOR, and adaptation towards that block will keep the hash value h and the tag TOR unchanged. Consequently, this means that each tag is uniquely bound with the one block, and hence uniquely bound with the block's chameleon hash value. Let's show how we can use this observation to change the full CR security. Here we show the winning condition of full CR. Firstly, we will split the condition that TOR star h star m star not in the set Q into 2 sub cases according to whether tau star M prime star is in Q. And then we change the conditions further based on the second observation, since tau star is uniquely bound with the hash value H star. Note that we can make this transformation only when the second observation holds. And besides, we add a restriction for the adversary's adaptation queries. Namely, there should not exist tau H1 and tau H2 in the set Q with distinct H1 and H2. We can add this restriction due to the second observation, since tau is uniquely bound with the hash value H. And our third observation is that all adaptation queries towards a specific blocks are typically made with different messages. In fact, we can ensure this by appending a counter to the message. Consequently, we can assume that all messages with respect to a same attempt in adaptation queries are different. Based on the above three observations, we finally arrive at a new security notion for tagged chameleon hash called restricted collision resistance, or restricted CR for short. Note that this restricted CR is strictly weaker than the full CR, since it makes more restrictions on the behavior of the adversary. Consequently, a tagged chameleon hash with restricted CR should be easier to construct. On the other hand, in the application of a redactable blockchain, the above three observations hold, and we can prove that restricted CR provides the same security guarantee as the full CR. In this case, tagged chameleon hash with restricted CR also serves for the redactable blockchain. So now the questions we considered can be changed to, can we design a post-quantum tagged chameleon hash with restricted CR in the standard model? And now we will present our tagged chameleon hash constructions from the lattices. Our tagged chameleon hash is constructed as follows. Its public of the metric to hash a message M, we will first sample a string Y, and then we define a circuit C, which equals 1 if and only if the PRF value on tau M equals Y. Next, we compute a matrix APRF by homomorphic evaluations on the circuit C, and the hash value H is computed as a concatenation of A and APRF times a small vector E. The randomness includes the string Y and the short vector E. To adapt a hash value H to M prime with respect to a tagged tau, we also first sample a string Y prime, and we define a circuit C using tau M prime and Y prime, and compute matrix APRF prime by homomorphic evaluations. Here, our goal is to find a short vector E prime such that the concatenation of A and APRF prime times E prime equals the target hash value H. And this can be done by pre-image sampling with lattice trapdoor TA. We can prove the restricted CR of our tagged chameleon hash based on the cis assumption. Here we give a high-level overview of the security proof. Recall that the adversary can make multiple adaptation queries and receive the corresponding randomness R prime, and the adversary aims to provide a valid collation to satisfy the winning conditions. During the reduction, we will embed an instance of the cis assumption into the matrix A, but there are two problems to be solved. Since A will be embedded as a cis instance, the trapdoor of it is unknown. So the first problem is how to compute the short vector E prime without knowing a trapdoor of A. The second problem is how to derive a valid solution to cis if the adversary succeeds in provide a collision. To solve these problems, we resort to a partitioning strategy implemented by homomorphic evaluations and PRF. We will embed the PRF key K in matrix AI by computing AI as A times Ri plus Ki times G. Here, Ri is the randomly chosen short matrices, and G is the gadget matrix. Besides, for each adaptation query, we compute Y prime as a PRF value of tau M prime. Then for adaptation query, the circuit C evaluates to 1. And in this case, the homomorphic evaluation on C gives us a gadget trapdoor. And we can use it to compute the short vector E prime without the trapdoor TA. This solves the first problem. As for the second problem, the winning conditions make sure that we can always find collisions tuples from the adversary's challenge or the set Q, such that the circuit C evaluates to 0. Consequently, we can derive a valid cis solution from these tuples and solve the second problem. We show two instantiations of our construction. First, by instantiating PRF with a LWE-based one, we obtain a concrete tagged chameleon hash from cis and LWE in the standard model, solving the question we considered. Besides, we note that if we replace the homomorphic evaluation and PRF with random oracle, then we can obtain a second instantiation in the random oracle model. This instantiation is very efficient, and moreover, it enjoys tight restricted CR based on the cis assumption, which may be of independent interest. And let me conclude this talk. In this work, we propose the concept of tagged chameleon hash and show that a tagged chameleon hash with restricted CR serves for secure redactable blockchain. And we show two constructions. One is in the standard model, and the other is in the random oracle model. Both are from lattices and without using NISIC proofs. That's it. Thanks for your listening. And if you have questions, you can contact the authors. Thank you.
Yeah, sure. I just prepared. Which one? PKC. No. Excuse me. Where are the slides?
They should be. Sorry, desktop is in. But there is this.
Oh. Okay.
Yeah,
Must
sorry,
be
that my bad. It's Tuesday 14th.
okay. Cool. Thank you. You will schedule. So just yeah. You tell me when I need to start. Can I move this?
I don't even know how you move that. So not maybe rotating everybody.
That's best I could do.
That'll show up on the recording.
Yeah.
Show up on the
Okay.
recording.
That's good. So it's default.
Next talk, analyzing Hash&Sign signature by Beltran, Beltran, and Simon Bastikian, and
Sure.
Shin.
So this is a joint with Bertrand. I think everyone knows here what digital signature schemes are, but just as a refresher, so digital signature schemes includes a signing algorithm and a verification algorithm. The signing algorithm takes a message and outputs a signature, and it has some secret key embedded in it. And the verification algorithm has a verification key embedded in it and takes a message and the signature and either accepts or rejects. Now we're gonna omit the generation algorithm for this talk because we're not gonna talk about it for simplicity. Now, Hash&Sign signature schemes existed forever, and probably everyone also studied that in the first introduction to crypto course. It's basically an engineering technique where you take a digital signature scheme and you say it's a Hash&Sign signature scheme if there's a composition of the hash function and the core signature or core verification inside of those two algorithms. Now, the idea is that the message enters the signature scheme, like take your signing algorithm, it gets hashed into a hash value and gets introduced now this hash value into the core signing, which actually outputs the signature. But what we're interested in this talk is not in the engineering technique, but mostly in the functionality of this. Now, we went through lots of different signature schemes, Hash&Sign. Well, different signature schemes, either standardized or yeah, most of them are standardized, either in the ISO or by the IETF or so on. And we could classify these signature schemes into two, either Hash&Sign, which includes PKCS, full domain hash RSA, VLS, ECDSA, which is American, the Korean KCDSA, the Russian Ghost, and the Chinese SM2, and non-Hash&Sign signature schemes, which actually do not fit into this kind of syntax, which is basically more of an interaction between, say, the core signing and the hash, or core verification and the hash. So it's more of an interaction. So these, we are not going to consider them. We're not going to talk about them today. We're going to talk about the left-hand side lists. So what do I mean by we're interested in the functionality of Hash&Sign signatures? Just to introduce the terminology, as I said, there's a hash function that includes that inputs a message and outputs a hash value. A core signing, which is a keyed algorithm that inputs a hash value and outputs a signature. And the core verification, it's a public keyed algorithm that inputs a hash value and a signature and outputs either yes or no. And we're interested in the functionality. And by this, we mean that practitioners actually love Hash&Sign signature schemes because they allow, it's easy for them to be capable of separating the hash and the core routines. And this reflects two different entities performing different tasks. And I am not crazy, I swear to you. We went to different libraries, crypto libraries, and we saw that like many of them actually implement dedicated API for separating the hash and the core signing. One of them is gcrypt, the other is Boring SSL, which actually has a core signing algorithm for ECDSA that takes only fixed length messages. So basically the hashing is done by someone else and you just plug this inside of the library, or inside of the signing algorithm. Or also standards have different standards, either supported or are discussing the standardization of some way the separation of this hashing and the core signing, whether it's PKCS 11, RFC 8032, or there has been a discussion on the PKC forum about doing this kind of separation for post-quantum signature schemes. Now, what are actually the application of this separation of the hashing and the signing? One example would be to have smart cards or HSMs or TPMs, which performs the core signing. And there is an external host computer that actually delivers the message. Now, if you take, for instance, a smart card, but like the ISO standards, basically, if you calculate, if you want to transfer 10 megabytes of message into the smart card, it takes around 12 minutes. So what they do usually is that you would like to hash the message and then send it directly into this kind of smart card that actually computes the core signature. Another application would be having complex implementation that include big number arithmetics, optimized assembly instructions, side channel attack protections, and this performs the core signing or core verification. And the message is provided by an external API that delivers this to the internal. Now, you don't want to copy a huge message into this kind of core routines that actually, because you don't want to implement all the assembly code for handling super long messages and so on. So you deploy this kind of separation of hash and sign. Now, the question is, now we see that it's important to, well, the community or several kind of libraries do separate this hash and sign. But the question is, what about the security of this? What does it mean to separate the hash from the core signing? And is this secure? What if the hashing is malicious? So we look into the security of those different schemes that we saw earlier, left-hand side. And we asked ourselves this question, what about the security? And we introduced this new notion we call HUF, H for hash and UF for unforgeability. And if you know the basic unforgeability, then this is quite straightforward. So basically the adversary here has access to a signing oracle, which takes as input not arbitrary long messages, but hash values. And this oracle outputs a signature over this hash value. Now the adversary has to come up with a message signature pair such that the hash of the message is fresh and that this message signature pair is valid. More specifically, so I guess, like if you know the unforgeability, this is straightforward. Once again, HV, like in the normal unforgeability, is replaced by a message. And here the freshness, like in the normal unforgeability, this freshness is on the message and not on the hash value of the message. And more specifically, the signing oracle here contains or runs the core signing. Now, the basic first question is, what's the relation between HUF and UF? On the one side, I have a malicious hashing, and on the other side, I have a benign hashing, let's say. Do they imply each other's? What happens? And we were interested mostly in the UF, like the unforgeability, of course, implies HUF, but the question comes in the other direction. What happens if the hashing is malicious? We came up with an example, artificial example. We proved that HUF does not imply UF, but we also studied real-world examples. One of them is BLS, we show. So just to recap, how BLS works. So you define a cyclic group G. You define a hash function that maps arbitrary long messages into the group elements. And then you have a pairing E, and the signing works as follows. So you hash the message and the output, the hash value is raised to the X, which is the secret key here. And then this is the signature. And for the verification, you hash the message again. The hash value is plugged with the signature into this pairing. And you compute the equality between the hash value and the public key, whether it's equals to the pairing of the signature sigma and the generator G. And this accepts or rejects. So this is BLS. Now we know that BLS, which is basically the gray boxes, is UF secure, but actually it turned out that it's not HUF secure. When the hashing is malicious, it's insecure basically. And this means, so the attack goes as follows. You have this adversary, it picks a message, any message. It picks also an exponent R. It computes internally the public operation hash of M, and it masks this hash of M with G to the R. It sends this hash value to the assigning oracle, which outputs the signature sigma. And now it delivers as a forgery the pair M, comma, sigma divided by G to the X, which is the public key, powered to the R. And if you check it like maybe 20 seconds, you figure out that this is a valid forgery. And it's on a fresh hash value because hash of M has never been asked to the signing oracle. So actually, we didn't only study BLS, but it turned out that also RSA full domain hash and PKCS v1.5 is insecure in the HUF model. And you were wondering whether the other schemes here are secure or not. So just to give you a glimpse, we studied ECDSA and we figured out that there is a reduction between, we were capable to reduce HUF to UF for ECDSA case. The advantages are as follows. Basically, yeah, the advantage of ECDSA in the HUF was less than the advantage of ECDSA in the UF, plus some negligible term. Here, G is the size of the group, and then Q is the number of queries that the adversary is allowed to make to the oracle. And so this is, I guess, it's fortunate because this means that all of the implementations of in boring SSL or Gcrypt or so on are actually secure, right? So we figured that all the other schemes are actually secure in the HUF. So whether ECDSA, ECKCDSA, Ghost, and SM2. And we thought that this is like not the end because like now what does it mean? You give me a Hash&Sign scheme and then I'll have to come and study it and see whether it's secure or not. So we thought of, is there any generic method to transform, to basically apply this kind of method on the Hash&Sign signature scheme and make it secure in the HUF model? And the answer is yes. So we propose this kind of generic method that applies to all kind of HCS signature schemes, where the hash function is a Merkle-Damgard construction. So I'll tell you why this method is also nice, but just to recap, what's a Merkle-Damgard construction? It's a sequence of compression functions. Each of them takes a message as input and a chaining value, and outputs a chaining value. The first chaining value is called an initialization factor, and the last one is the hash value, actually. So the typical way of breaking down Hash&Sign signature schemes, whether in the implementation of boring SSL, is to do as follows. So you have this hash function, you separate it completely from the core signing, and this is the separated Hash&Sign implementation of boring SSL, for instance. But this is not a generic way to apply to all kind of schemes and see whether it's secure or not. And what we propose is to do it differently. Rather than adding an extra hashing primitive or so on, we don't do any of those. And what we propose is to cut down the Merkle-Damgard chain such that the last compression function is actually executed inside of the sign, meaning that actually now your whole message, which is like 10 megabytes or several gigabytes long, is compressed into one chaining value and one last block. And these are transmitted to the core signing, which performs one single compression function and the rest of the core signature. So why is this interesting? Because why is it better than the double hashing? Meaning that why is it better than I hash my message and I plug this hash inside of my classical ECDSA scheme and then, well, first of all, you can see that it doesn't need any extra cryptographic components, but also it's backward compatible, meaning that if I take this kind of if I take this method of breaking down my hashing and the core signing, and I generate a signature with it, and I give this signature to a different person, different library that implements the real classic ECDSA, then this signature can be verified. Whereas if I double hash, meaning if I hash the message and then I insert this hash into the ECDSA, which hashes the hash and then signs it with the core signature, then this output signature is not verifiable by any other person who really implements the ECDSA scheme, the classic one. Additionally, also, if you basically double hash the message, you need to agree on a secure hash function. You need to transmit this kind of, you need to agree with your verification peer on what kind of hash function to use and so on and so forth. Whereas here, like, it's just pure, basically. So that's everything, I guess. Yeah, to conclude, so we investigate the functionality of Hash&Sign. We introduced new security models and a new method for kind of splitting this hashing from the signing in a secure manner for the Merkle Dankort cases, of course. And for a future work, it's good to study this kind of separation of the hashing and the core routines for non-hashed and signed signature schemes. So for basically non-natural way of splitting this kind of hash for schemes that have a non-natural way of splitting the hash and the core routines. And that's it for today. Thank you a lot.
So in your lecture, the notion of security. So that if an adversary can find out collisions with a hash function, then it is in real world it should be insecure, but in your motion, there's a possibility where even if the adversary computes collisions with a hash function, in the challenge phase they should provide a new hash, right? So your notion is probably not capturing that.
So yeah, so this exactly. So if you find a collision in the hash function, actually, so in the normal notion, you break the scheme, and in this notion is actually you still can you cannot actually win, because what you care about is the essence of the scheme, which is the signature, not the hash function, right?
Okay. So that means so maybe then there's a separation that if the scheme is HUF, but you can always it's probably not pure because of so you can compute consider an artificial hash function which has collision. That is HUF secure but not EUF secure.
Yeah, okay, sorry. So I mentioned earlier the implication of UF and HUF. I meant, yeah, so UF plus collision resistance is by HUF.
You mean the UF of the core component?
UF of the full scheme.
Oh.
Of the full scheme. So basically this the gray box here. Gray box here. Yeah.
One question.
Mhm.
When you define your HUF, you suggest the hash implementation may be malicious, but in the signing scheme, there are signer and verifier. In yours, and both signer and verifier have access to the identical malicious hash, or only the signer or only the verifier.
So in this definition, so if you allow the hashing of the verification to be malicious, which we've never seen in any other implementation, your security basically reduces only to the core signature scheme, meaning that suppose you have the hashing that's malicious, whether in the signing oracle or in the verification oracle. So the verification oracle takes a hash value, or suppose you forget about this, okay? And what you care about, you forget about this. And what you care about is to give a hash value here and the signature to the to the challenger, and you see whether you win or you lose, whether the signature of the hash value is actually valid and it's new.
I mean, in the real world, for require message, right? As a require, I can see the entire message. And if the just the signer has the malicious hashing implementation, but as the require has the honest hashing implementation.
Yeah.
So what can you got just recompute the hash?
Yeah, you can. You can recompute the hash.
So why the scheme will be insecure?
I'm not saying it will be insecure. I'm just the actual our definition actually allows the verifier to hash the message, and this is why the message and the signature is output, right? And it doesn't say anything about the insecurity. It's just a notion, right? Sure. If I replied exactly to what you want to say, like to your question, we can take it. Fine.
One question.
Yes.
We can consider your result in opposite way. The HDSA in the HEF scenario, then it implies that HDSA is not secure in the general EFC.
No, actually not, because you can take it's not true. So what you can do is you can take a signature scheme, an artificial one, which takes a hash function that's collision resistant, and that it leaks. So the core signing leaks the key if the hash value is equals to 0. Okay. So now in HUF, this scheme is actually broken, because you can just query the signing oracle on this 0-bit string, and then your key is leaked, and then you can forge. But in the normal unforgeability definition, then this scheme might be secure, because if you combine the collision resistant hash function with this scheme, then this core signature, then this is fine.
Yeah, but ECDSA is not fully secure in the
Sorry?
Yeah, okay. Anyway. Yeah, so this might be okay.
So this is proven secure in the Verschkilt and Pottering paper, where they model this kind of algebraic transformation inside as a random oracle, right? And this is proven secure in this kind of paper. So once again, this is a reduction, and this part is proven secure in the IT Pilz and Patch paper, but it's proven.
So function time is right in the quantum number of by the same time change.
Yeah, thank you for the introduction, and welcome to my talk. My name is Haruhisa, and this is a joint work with Keita Kusagawa. My talk is about the proof of security of Hash&Sign. Let's get started. Here's the table of contents, and I'm going to start from the background. The NIST PKC standardization is ongoing, and last year, NIST has issued additional call for the digital signature to improve the diversity of a portfolio. For this goal, many schemes have been proposed. Among them, the Hash&Sign is adopted in many schemes. The Hash&Sign is one of the popular and general frameworks to build signature along with the fiat Shamir. Actually, 14 out of 40 candidates adopt the Hash&Sign. Here's a list of Hash&Sign signatures. Lattice, multivariate, and code are well-studied area in cryptography. So I guess Hash&Sign signatures must be promising candidates for this scope. So what is Hash&Sign? I use a different introduction. I'd like to explain from the beginning. The core of Hash&Sign is a drop-down function. In the key generation, F and I are generated. F is a hard invert function. This is a verification key. And I is a trapdoor or F. This is a secret. In the signature generation, R is randomly chosen and compute a hash value of R and M. Using a trapdoor I, we compute a preimage X of the hash value. R and X consider signature. In the signature verification, we compute H bar M and F of X and check if they are the same or not. If they are the same, the signature is verified. There are three variations. The deterministic Hash&Sign doesn't use R at all. The probabilistic Hash&Sign uses a random R. The probabilistic Hash&Sign with retry executes the signature generation like this. After generating a preimage X, we check if this X is valid or not. If it is valid, we output X as it is. Otherwise, we take another R and do the same thing. And we repeat this procedure until we can get a valid X. Actually, it's easier to be a signature. For example, surjection is not required for the probabilistic Hash&Sign with retry. Even if it is not surjection, we can take the hash value until the hash value is inside the range of the function f. For this kind of convenience, it must be harder to prove the security. Here, I want to introduce some definitions. The EUF CMA for existential unforgeability against chosen message attack. The adversary has access to the signing oracle. He can make queries to the signing oracle to make signatures for arbitrary message. And he tries to forge the message and signature. There's another definition called EUF NMA. NMA stands for no message attack. As the name suggests, the adversary has no access to the signing oracle. The non-invertibility is a security definition for the trapdoor function. The adversary is given f and W chosen y hat and tries to find x star such that f of x star equals to y hat. There's another definition called one-wayness, almost the same, but there's difference in the way of choosing the challenge. In the one-wayness, x is randomly chosen and y hat equals to y f of x. In most of the cases, we use non-invertibility in the security definition of the trapdoor. The Hash&Sign signature is provable secure if there is a reduction from non-invertibility or collision resistance. And we need to assume the random walk model or quantum random walk model. I just say ROM or QROM. QROM can modelize a real-world adversary who can implement hash function in the quantum computer. Therefore, post-quantum signatures must be provable secure in the QROM. However, secure signatures in the ROM are not always secure in the QROM. There's a separation result. So we need to check if there's a reduction in the QROM, even if there is in the ROM. Here's the current status of the provable security of the Hash&Sign. As for the deterministic Hash&Sign based on collision resistance, including the GPV framework using the Falcon, there are reductions both in the ROM and the QROM, and they are tight. As for the probabilistic Hash&Sign based on non-invertibility, there are reductions both in the ROM and the QROM. However, there is a problem in the security reduction in the QROM because the requirement for this reduction is kind of strong. PSF is required. PSF is preimage sampleable function. That is a special trapdoor function with some conditions like fx is uniformly distributed and f is a surjection. Due to this requirement, the applicability of this reduction is kind of limited. As for the probabilistic Hash&Sign with retry, we have a reduction only in the ROM proposed by Sakamoto et al. However, their proof is flawed. We've had mistake in the security proof. So currently, before my study, the probability Hash&Sign with the try is not proof of secure at all. So, ladies and gentlemen, I'd like to introduce our new security proof. This is overview. This is reduction from non-invertibility to EUSMA in the QROM. This reduction consists of two reductions. I'm going to talk about these two reductions separately in the following slides. And this is the security bound. The advantage for EUFCMA is bounded by the advantage for the non-invertibility. So if the trapdoor function is non-invertible, we can say that there is a EUSMA security in the signature scheme. And there are three additive terms. As for these last two terms, we need to set the bit length of R large enough to make these terms negligible. As for this term, epsilon PS, I'm going to define later. What I'd like to say here is this: to make epsilon PS negligible, outputs of trapdoor must be simulatable. So what is the definition of simulatability of a trapdoor? I'd like to introduce this kind of game. The adversary tries to distinguish these two oracles, sample 0 and sample 1. The left one is sample 0, which uses trapdoor. It's kind of an honest generation of preimage. Y is randomly chosen, and using the trapdoor I, this oracle generates a preimage X of Y, and then do the same thing until X is valid. And the right one is the kind of simulation. X is generated by a sample domain function, which is a function to simulate preimage sampling of trapdoor. So this one doesn't use trapdoor at all. So, and epsilon PS is an advantage to distinguish these two oracles. If epsilon PS is negligible, we can simulate trapdoor without using trapdoor. And negligible epsilon PS is kind of a weakened condition of PSF. Actually, PSF becomes much more than this one. And we can use a computational bound for epsilon PS. And what we can say here is this: some the functions are not PSF. Actually, it's really difficult to build PSF outside lattice actually. And however, there are some the functions that are not PSF but satisfy negligible epsilon PS. Before going to my proof, I'd like to introduce a flaw of the existing proof by Sakamoto. They assume the negligible epsilon PS and try to simulate the sign oracle by using the programming or reprogramming. They have the same meaning, but the same effect. But I'd like to use the reprogramming here because I use reprogramming in my QROM proof later. Okay. This is a modification of the signing oracle. X is generated by sample domain function, and the random function H is reprogrammed such that H of M equals to f of X. But this is really bad the situation because Fx is not necessarily uniform. If we assume PSF, Fx is always uniform, but we don't assume that. So the function H is no longer a random function due to this reprogramming because the output of H is biased due to this reprogramming. We need additional steps between these two oracles. Here's our answer. This is actually the reduction from the EUF NMA to EUF CMA, no message attack to chosen message attack. We added two additional steps. Step 1, Y is randomly chosen, and the random function is reprogrammed such that H over M equals to Y. This is feasible if this R R is kind of freshly chosen here. This kind of reprogramming is feasible in the Chrome using the tight adaptive reprogramming. In step 2, we cancel unnecessary reprogramming during retries. Then the reprogramming only occurs only at the end of the signing oracle. And this kind of canceling is feasible if we prohibit the adversary from making query to the points that were used like here. And this canceling is feasible using the semi-classical O2H, which is very popular technique in the Chrome. And in step 3, we don't use a trapdoor anymore. X is generated by sample domain function. And if we take a look at these two oracles carefully, we realize that negligible Epsilon PS enables this kind of simulation. Okay, in the end, we can simulate the sign oracle without using trapdoor. As for the reduction from non-invertibility to EUF NMA, we use a measure and reprogram technique. And this technique results in this kind of bound, which has quadratic loss. And here's our view. The adversary for non-invertibility, given the challenge Y hat, simulates the EUF NMA adversary like this. First, he measures J's query and the measurement result is R prime prime. Actually, J is chosen in the beginning of the game and reprogram the random functions like that H of R prime and prime equals to Y hat. Doing this measurement and reprogramming, this adversary can give information of his challenge Y hat to the EUF NMA adversary and get a kind of premesh X star of Y hat like this. And we applied our proof to some signature schemes. Here's our view. As for the probabilistic Hash&Sign based on non-invertibility, we added another proof in the Chrome, and this proof doesn't require PSF. In a sense, as we relaxed the requirement for this reduction. Due to this relaxation, we can prove the security of wave and mile, which are included in the candidates for the NIST PKC standardization. As for the probabilistic Hash&Sign with the retry, we have reductions both in the ROM and the QROM. Due to this, we can prove the security of PROV and QROV. They are also the candidates. Fortunately, PROV and QROV use our security proof in the specification. Unfortunately, wave and mile don't use our proof. I hope they will use in the next version of the specification. Okay, summary. We propose the first security proof for the probabilistic Hash&Sign with the try in the ROM and the QROM, and our proof has wide application, and it has big impact of the NIST PKC standardization because some of the signatures are provable secure due to our work. And we extended our proof to multi-key setting, multi-key security. Due to limited time, I didn't talk about this one. If you are interested, please read the paper in the e-print. Thank you for listening.
So I see that there's a bit of some square root losses.
Yeah.
So I guess there has been quite some work on the one mass, like to make come out more tighter variants. So is it possible to like make your book? So there was some MRM measure we want to measure. So
Yes, thank you for the question. It's a very good point. Yeah, I know that there are some techniques to make better bound, but I think in this application, semi-classical or original auto-edge are only techniques we can use. And actually, it's not necessary so much because what we just have to do is the make this arm larger, and we can make these two terms negligible.
Yeah, but if there's no square root, then it's more.
Yeah, I understand what you're saying.
But the MRM can be applied to very special setting.
Yes, yeah, exactly.
That's case is in C. No, I'm not sure about the link notes because the other side. Yeah. It's your action loss improved when classical
So
reduction
a mathematical,
going to better.
so you're talking about this term?
Yes.
In the classical realm, this is linear.
Linear.
Yeah, it's a QRO is added on the advantage for no invertibility. So it's just
you can remove the square. Just remove the square.
yeah,
Oh,
yeah.
Okay. Thank you. So